Chapter 8, Linear Regression. This is the process of creating a line of best fit. In this scatter plot, we have protein values and fat values from 30 items on the Burger King menu. Obviously, this doesn't make a straight line, but it's straight enough. I can eyeball a line of best fit through these points. And we would say that the association between these two variables is positive, linear, moderately strong, with no unusual features. Now, regardless of how I draw my line of best fit, there's always going to be some points above that line, other points below that line. Thinking back to your algebra class, the most basic equation that we could write for a straight line was in slope-intercept form, y equals mx plus b. And we're going to stick with that in statistics. We're just going to rearrange it a little bit. So let's think of it as y equals b plus mx to start. And then just note that we're going to change a few things. So first off, the y is going to get this symbol on the top of it, a little party hat. The b is going to have a 0 on the bottom, called b sub 0. And instead of m, we're using b sub 1. Now, the statistical name for this variable is, funnily enough, y hat. Okay, and the reason it has that little symbol, that hat on the top, is because it's a predicted variable. Remember, this is the equation for the line of best fit. It's quite likely that none of our actual data points are actually on the line of best fit. So when we plug in a point, we're getting an ideal point, something that's not real data. Okay, anytime we see anything with a hat on it, it's not real data. If we were using actual data values, we would just use y without the hat. So being that we have this line of best fit, and then we have our actual data scattered around it that doesn't fall on the line, each one of those actual data points has something called the residual. So the data point has its own y value, the real y value, and then on the line we have a predicted y value, whatever the y value is at that point for the x value on the line. And the residual is just the observed minus predicted, the actual y value minus the predicted y value. Here's a visual representation of what a residual is. If we were to take any of these points, let's say this one here, okay, note that it's above the line. This has a positive residual because if we take the actual y value of that blue point and we subtract what the predicted value is at that same x value. So y minus y hat, the y hat is the point on the line right there, and we just subtract those two. Okay. A negative residual means that our predicted value is too large. We have an overestimate. In this case, our predicted value, which is on the line there, is too small. It's an underestimate. Okay. Here is what they're talking about in this one on the bottom. So it says the estimated fat of the Burger King broiler chicken sandwich is 36 grams. Estimated, that's the predicted value. That's that y hat. The actual value of the fat is 25 grams. It's always actual minus expected, so we're doing 25 minus 36. We get a negative 11 for the residual. Now, there are a lot of reasons why residuals are important. The first of which is because this is really what's used to create the line of best fit. Anytime we draw a line through the scatter plot, we have a number of residuals. Let's say we have this green line here. We have residuals for all of these points. If we were to draw a different line, any different line, all these residuals are going to change. Okay, so let's say we have this red line now. We can see over here, this one got a lot smaller. This one got a little bit bigger. This one got a bit smaller. So all these change. Some get bigger, some get smaller. The line of best fit is the line that minimizes those residuals. Now, another thing to note is that we always have some points above the line, some points below the line. Some residuals are positive, some are negative. If we were just to take them and add them together, they're going to cancel each other out. We're going to end up with an average of 0. So instead, what we have to do is we have to square them all first. That changes them all to positive numbers, and then we add them together. This is why a regression line or a line of best fit is also referred to as a least squares regression line. All right, let's do some actual math for a change. So in a regression line, we can calculate the slope and the y-intercept given certain characteristics about our data. So we need to know what the correlation value is, and we need to know the standard deviation and the average for both the x variable and the y variable. If we have that information, we can calculate our own regression line. So the slope, B1, okay, we always want to find this one first, is that correlation value times standard deviation of y over standard deviation of x. Remember, y is always on top, just like when we found slope back in algebra, it was rise over run. Okay, sometimes you'll see this written like this instead, r times standard deviation of y over standard deviation of x. Another way that we can think about this, which we'll have to think about it like this in some ways, for every one standard deviation we move in the x direction, we're going to move our standard deviations in the y direction. Now, when it goes to calculating the y-intercept, we take what we got from the slope, we're plugging that in down here, along with the averages. This is y bar and x bar. Anytime we see the bars there, we're talking about the averages for those variables. So here's the actual regression equation for this Burger King data. We're taking a menu item, plugging in the protein, and we're getting out a predicted fat value. That's why that fat has the hat on it, fat hat. All right, so what does the slope 0.97 mean? It means for every 1 gram increase in protein, the predicted fat amount will increase by an average of 0.97 grams. Keep in mind that the line of best fit is really just idealized. In actuality, we have a lot of scatter around this line. Okay, so these are average changes in the line of best fit. What are the units? When you're asked about units in a scatter plot, just think back to algebra and slope. It's rise over run. So we have units for the vertical axis, that's the rise, over the run, units for the horizontal. So it's grams of fat per grams of protein. How much can you expect the fat to increase if the protein increases by 2 grams? If the protein were to go up by 2, the fat would go up by 2 times that slope, 0.97, which would give us an increase, an expected increase of 1.94. Keep in mind that in actuality, we would see variation around that number. Lastly, what would the predicted fat content be for a Burger King broiler chicken sandwich with 30 grams of protein? We're just going to plug that in, and we get 35.9 as our predicted fat content. Next example, a scatter plot of housing prices in thousands of dollars versus house size in thousands of square feet shows a relationship that is straight with only moderate scatter and no outliers. Correlation between the price and the house size is 0.85. So to start, let's just picture what this would look like. So we would have a horizontal axis. As for the explanatory variable, the size would probably go down on the x-axis. Price is being explained by the size. All right, so if a house is 1 standard deviation above the mean size, how many standard deviations above the mean would you predict its sale price to be? This goes back to this equation on slope, r times the standard deviation of y over standard deviation of x. Thought of another way, every 1 standard deviation we move in the x direction, we're going to move our standard deviations in the y direction. So that being said, if we're 1 above the standard deviation, 1 standard deviation above the mean in the x direction, we would be 0.85, which is the correlation value, standard deviations above the mean in the y direction. And in this last example, we're just going to find the regression equation given mean standard deviation for both variables and the correlation coefficient. We always want to start with a slope since that's used to find the y-intercept. Slope is r times those standard deviations divided. Plug it all in, and we get negative 36.21. So this has a negative association between these two variables. Y-intercept, use the slope along with the means from the two variables, and we get 2,266.6. And just to stress, when you write this equation, having this hat on the y is absolutely imperative. If it's not there, you will lose points.